Okay, so I'm going to do it twice, once for the engineers and once for the Mathcad geeks. So here is the Mathcad for the distribution of seismic loads via a stiff diaphragm into our concrete shear walls. So we set out the diaphragm dimensions, so width and length, 20 meters and 10 meters, and we have our story height set as 3 meters. We apply our seismic force in one direction, so in the x direction it's 100 kilonewtons, and then we can take 30% of that and apply that in the y direction. We'll assume for simplicity that the application of the load is in the center of the floor, which is assumed to be where the center of the mass is. We put in some properties for the concrete grade, and the modulus of elasticity is 25 GPa, and the modulus of rigidity as 10.4 GPa, which we're now deriving from the modulus of elasticity. We put in our strength reduction factors as required, and then we move on. So here is the wall layout we showed before, and then we've got two exercises, one in the y direction and one in the x direction. So we enter the coordinates for the positions of the walls and the length of the walls in the x direction. So the first wall is 6 meters long, it's 200 millimeters thick, and it's 100 millimeters off the x-axis. And we're telling us here that it's basically a cantilever wall. It's got a moment out at the base. The next wall has got moment top and bottom, and the third wall is a simple shear wall. So we then work out the wall properties from that. So we've got the lengths of the walls, so 3 and 4, the areas of the walls, the second moment of area for the walls, and then we have the stiffnesses derived for each of the walls depending on whether it's a shear wall, whether it's a cantilever wall, or whether it's a fixed wall, top and bottom. And we repeat the exercise in the other direction. Moving on, we then calculate the wall stiffnesses and the total wall stiffnesses in each of the directions. Here's the y direction, and then we have walls in the x direction for wall stiffnesses and total wall stiffness in the x direction. From that, we can derive our center of rigidity by summing the stiffnesses and the eccentricities and divide it by the total stiffness. So that gives you the resultant x offset, and similarly a y offset for the walls in the x direction. So then we derive the wall offsets from the center of rigidity as Rx, and so we have 4, minus 4, 3.5 and 15 for the walls in the y direction, and this is shown in this diagram here. Then we can tot up the eccentricities and apply the accidental eccentricity. So here is our inherent eccentricity, but here we're adding our accidental eccentricity as 10% of the dimension in that direction. Then we look at the rotational stiffnesses of the wall systems. So for each wall in turn, we work out what the torsional stiffness of the wall is, add up the grand total, and then there's the sum of the squares to give us the total for the system. And we do it in the y direction and then do it in the x direction and tot up the total together. So that is the total torsional resistance of the whole wall system. Now we look at distributing the forces, and so as we can see, the distribution of shear forces is relatively simple. We take the stiffness of the particular wall divided by the total and multiply it by the applied load in that direction. So we do that for the y direction, and here we're doing it for the x direction. And we do a check. Is the total applied shears equal to the applied loads? And here we've got HY is equal to 30, which is equivalent to the applied load in the y direction, Similarly, in the x direction, the total of the shears is equal to 100, which is the applied load in the x direction. Now we look at torsional moments, and they work out for the two eccentricities and the two directions. How do we distribute those? Well, we look first of all in the y direction and use that formula that we showed above to distribute a horizontal shear. So we end up with a number of different load cases. So first of all, we'll look at load case 1, which is the force in the y direction with positive eccentricity, and distribute using this formula here. So it's the rotational stiffness for the individual wall divided by the whole total multiplied by the moment. Then we've got load case 2, force in the x direction with negative eccentricity. So those are those two load cases here, and that's where we've distributed the load applied in the y direction around the shear walls. Then we've got load case 3, which is a force in the x direction with positive eccentricity. And then we have load case 4, which is a force in the x direction with negative eccentricity. So there's 4 potential load cases there, and this is only looking at the force originally in the x direction with a complementary force in the y direction. There's 30% of that applied in the x direction. And so we then summarize the forces and get the grand totals of the total force in the walls in the y direction and the walls in the x direction. And that's it, nice and simple. I said I'd do it again, and I will do it again. So I'm going to show my working out for the benefit of the Mathcad geeks. So we go back to the beginning, and let's make it a little bit bigger. So we put in our dimensions as we've shown. There's our wall layout. There's the basic properties for the walls, so the wall areas, the second moment of area, the wall stiffnesses for shear and torsion. So I've hidden something in here. How do we get the total wall stiffnesses? Well, because these are arrays, we need to create a matrix. And we need to create a matrix in each direction. So we start by defining how big our matrix is, and that's dependent on the length, the number of walls. So in this case, we've got 3 walls, and we start with initial value of 0 for the shear, and we populate this matrix. So in the 0 column, we have a number. The column marked 1, we have the length. Column marked 2, we have the thickness. Column marked 3, we have the area. Column marked 4, we have the x dimension. For 5, we allocate the stiffness, and we do an if. So if it's a fixed wall, we have this kind of stiffness. If it's a cantilever wall, we have a second type of stiffness. Otherwise, it's a plain shear wall. And then allocate that to the 5th column, and in the 6th column, we multiply that by the eccentricity from the x direction. So we repeat that exercise on the right-hand side. Similarly, walls in the x direction for wall stiffnesses. There is our table that we've just derived. And from that, we can pull out our wall stiffnesses is the 5th column in our matrix. And because our matrices are indexed from the number 0, we have the column here to populate the wall stiffness. And the wall stiffness multiplied by the x value is the 6th column. And we do the same for walls in the x direction, and then creating the sum total to create the final tables. So again, we're creating a matrix from the whole set of arrays we've already had and populating the tables. So here is the basic shear, and these are the 4 load cases, and then we're doing a comparison with the maximum of the loads in either direction to get our final figure, HY. Okay, so that was the Mathcad.